said, nice to meet you all, and I told Christian it's my first time here too. What I want to do today is actually talk to you about unikernels and try to explain what they are. I think Docker is probably known for containers, but less about unikernels. So I'm going to try to demystify it. So first of all, talking about Docker, I want to give you some numbers and stats and a little bit kind of where we're at. So the Docker project, which is run and maintained by Docker, has over 2,000 contributors at this point. We have a lot of Dockerized images, in fact, 400,000 Dockerized images. And we get so far we had over 3 billion image downloads. By the way, just a year ago, this number was 1 billion. So as you can see, the growth is quite significant. In terms of our commercial product suite, it includes what we call an end-to-end CAS, which is container as a service. And we were kind of the way we think about it is if infrastructure as a service is too low and platform as a service PaaS is too high, CAS is kind of just right. In our ecosystem, we have over 300 partners, 350 partners, and actually one of them is Relic, and I want to thank Relic for hosting us here today. And just in our company, we are over 240 employees in many places. One of them is Cambridge, and again, the Unikernel team is over there. So in order to talk about unikernels and Docker and all of the above, it's hard not to talk about it without talking about how application development has been changing and how apps have been changing. And while in the past you would have big servers and big apps and normally dedicated servers to big apps, the way our apps written today are actually as a set of microservices that are highly distributed but are connected. What you end up with, though, is many hardware types and many app components, and you need to also move from dev to test to production, and you end up with what we call a matrix from hell. And how kind of containers and Docker are helping with this is that, well, what happened? Can you hear me now? You actually package it in small components, but they're very predictable and deterministic. It allows you to control your environment. It's that kind of everything that you need is contained in this one part. And as you move it from these different environments, you know what's in it, and you make it a lot more predictable. So we talked about microservices, but there's more than microservices that is changing today. There's actually multiple hardware form factors. There are clouds, and clouds make compute very accessible. There are private clouds, and now many companies have multiple clouds. There are also DevOps, which changed the way development processes have been working and the degree of automation that you have. And we already talked about microservices, and kind of Docker sits in the middle of many of these things. But really, maybe the point here to make is that those new types of environments and developments and app structures really call for a new set of tools and new way of thinking. So let me see which one, this one. So in January 2016, we announced that we actually brought into the fold a company organization called Unikernel Systems, and they have been working on unikernels for a while. And and I want to again today explain a little bit what are unikernels, and maybe kind of give a hint of where this is going. So in Docker, while it started as Linux containers relying on kind of the mechanisms that the Linux OS has provided to create containers. Where it's going is that we have been adding more and more architectures, more and more operating systems, and more hardware. In fact, just this last month, we had Windows CP5, Technical Preview 5, and soon we're going to have full support for Windows containers. And and then the community have also kind of risen to the challenge and ported Docker to many different hardware platforms. So, for example, we have a member of the community that showed an ARM support. In fact, they have this neat demo that shows that you can actually pack a lot of containers into an ARM processor. So definitely, there's going to be an evolution of the different platforms. So when you think about where we're going to have a lot of CPUs in the world, and where you think about where you're going to see a lot of these new form factors, it's hard not to think about this. And actually, how many of you have, I don't know, wearing an Apple Watch or some sort of a smart watch? Okay, there are quite a few. And when you think about it, actually in your home, you probably have quite a few of these kind of new form factors or new CPUs and new OSs. In fact, I was trying to count last night how many of different devices I have that have a CPU and OS, with some sort of an OS at home, and I stopped at about 40. It was actually pretty shocking. And it's all the way from TVs. Your new TVs are now connected to the internet. They have CPU, to the speakers you have at home, to smart appliances, not to mention the computers and the phones, the game console, your watch, all of it. And this is just the beginning, clearly, where this is going. And again, with that, with all of these CPUs and OSs distributed around your life, it actually brings a new set of challenges. And and some of these are, first of all, they inherit some of the existing system issues that the existing kind of way of building software has. So security, speed, the footprint is pretty big of existing, let's say, OSs. And there's an interesting thing that on one end, they're connected to the network. Most of your devices are connected to the network. On the other end, they're actually distributed and disconnected. So if you were to try to do a map of all the devices you have at home and which one is on, which one is off, where do you have them, where are they connected, it's going to be impossible to do. So, and it's unlikely that you updated OS in your fridge lately. So they're not really well managed or not really well updated. So it's kind of something that you need to have a little bit more intrinsically robust in order to be able to manage them. So I have the picture here of the kettle to remind me to tell you a story, how there's this company in, I think it was in London, that created these iKettles where they were you can actually turn them on with your iPhone or with your smart device. You can do outside of home, and they will wait for you. And actually, somebody was able to break into the kettles and get your Wi-Fi password. So like a very simple device that you think, oh, just making myself tea, and up being quite a bit of a security vulnerability. Then if you look at these devices, like you said, you kind of bring some of the old technologies as you create with them, and with that you bring some traditional challenges as well. So you can look at some of the big bugs that we had in the last several years, like Heartbleed and shell shock. And actually, many of them are present in those devices, except that you can probably think about these bugs as generational bugs. Is they're going to exist there for a number of these devices, and they will never be found or fixed because there's some out there in the wild. and there's no way to know what version is running where. So again, it's kind of a big problem. So now we are getting to Unikernel, and then again, that kind of, some of these new technologies let different people think about, well, how should you think about, what can you do to make inherently some of these OSs and devices more robust? So let me kind of first explain what happens in a traditional OS. So if you take a look at how your application is built, it's actually, it was going to be run on a kernel, and it's inherited from a lot of libraries. And, and there's actually a lot of goodness that is put there. However, you probably don't know exactly what's in these libraries and what's in that kernel. They're actually attaching to your application and are available there. So it's a very holistic approach. It's all like there for your app, everything that you need. However, if you take a look at what your app it actually needs, it's very small parts from all of these things. It's actually a very small part of the kernel. So a lot of the goodness of what's coming with the OS is actually never used by your app. So, so you can think about it this way. So while you need this from your OS, actually what comes with it is this. What your OS says, no, bring all of this with me. And, if you look at the size, and kernels have been growing over time. There's a nice graph that shows OS growth over time. If you actually look at the size, so Debian is 65 million lines, and out of that, the Linux kernel is about a third. So it's a lot of code. So again, how can we think about this a little bit differently, and how do we deal with the part of the iceberg that just comes for the ride? And this is kind of where Unikernel comes in. Unikernel is really a new concept. It's actually an old concept, but it's kind of a new concept. So if you look at, and by the way, that's kind of when you think this graph of the tip of the iceberg and what you need, then over time you actually need less and less, because as we talked about, if you look at how software is being evolving, is that you break things into microservices. So your app now becomes smaller and smaller, and it needs less and less. But the kernel becomes bigger and bigger and just kind of attaches itself to this like smaller particle. So the way to think about it is, what imagine to yourself is the concept is that you want to reduce the kernel to what you need, to the minimum that is needed, and take from your operating system just what you need. So how can we do that? And the way to do that is, instead of thinking about the OS as this holistic thing that you run in, you think about it as actually a set of libraries. So now there's a set of libraries that are available and that you can compile and link with your app. And the result that you end up with is the standalone Unikernel that includes your app and includes the kernel that it just needs. So I don't want to, it's a nice picture. I don't want to get too much into the details, but the result that you end up with is a highly specialized application. And in this case, I'm showing a single 64-bit address space. And because the Unikernels are compiled and they're not running in a system that has to deal with a lot of processes and schedulers, you end up with kind of a dedicated address space. And here's an example of a unikernel running inside a Zen hypervisor. And you end up with a single address space. It's simple. And you know where you are, which actually brings you a lot of advantages. If I wanted to show you like this app, that's a similar app, but inside kind of a Linux regular OS, I probably will need like multiple slides. So probably that's what you need to remember from this is that it's simple. And then again, like compared to how traditionally it will be with lots of scheduling. So just kind of want to explain here that the purpose of unikernels is not really to reinvent or remake the general purpose OS. And it's really a different goal. It's a different direction. So the idea is really to stop the growth and think of a different concept. So it's not like you will wake up and in 10 years, you'll end up with a big unikernel, right? Or a big library. What ends up happening is like you will continue adding libraries to your need, and your app will continue compile and link and just use what it needs. So it's really kind of a different way to think about it. By the way, there's, and I'm going to talk about more, but there's like multiple of unikernel projects, and even NetBSD has a project where they actually breaking the OS into libraries. Most of the unikernels are open source, and often they have, like a very easy to use license that go with them. So the unikernel that is part of Docker right now, and that team, along with the community, have created something that's called MeRaOS, and that's a very functional unikernel framework. It actually has more than 100 libraries already, and it distributed using OPAM. You can actually look at the site and find a lot of what you need there. It is written in OCaml. I don't know, how many of you heard of OCaml? Oh, okay, there's a lot. Which is a very good language for this purpose because it has static type binding, which means that you have to be very precise when you compile, and you have to do less work during runtime. So you end up with more security and faster speed. Now, MeRaOS is not the only unikernel, and many of the languages have their own unikernel. So there's an effort for Go, and there's an effort for other languages. So there's many of these unikernel libraries or OS libraries. And in fact, and I invite you to check later on the unikernel Wikipedia page, it has actually a pretty good list of these unikernels. One of the nice things about MeRaOS is that it actually allows you to get multiple targets. So what that means is it also kind of continue to explain why it's different from an existing operating system, is you can recompile and then, and very easily just change like the drivers or change what you need, end up with a target to a different hardware framework. And the APIs are designed in a way that you don't have to change necessarily your app. You just have to recompile it with the right component. So it was designed like this from the get-go. So, wow, this slide really didn't survive the transition. But it talks about the benefits of unikernels, and we have already talked about the fact that they're going to be small in size because you just drag what you need, and they're going to be faster. But there's also less code complexity, which actually reduces the attack surface. So again, inherently more secure. And because we talked about one address space, there's less context switching. So you'll end up with a much faster app. You can imagine if you had a web server built as a unikernel, how much more effective that would be than if you have it in, again, a generic OS that deals with everything else that's going on. And since you're not competing with others in your unikernel, then you have a very predictable scheduling. Now, having said that, you can even override the scheduler because you use like a specific library. If you need to do something more sophisticated, you can actually override the scheduler to do something else that you need. And it's kind of a classic, it's inherently an immutable infrastructure part, because if you need something new, you'll just recompile, kill the unikernel, run a new one. So you're not like continuously have increased the complexity of a running system, but you kill it, recompile, bring a new one. So maybe it will be good to give some examples here. And I chose completely 3 different examples, but hopefully that will kind of give a taste of it. And there's obviously, like we talked about IoT, and there's obviously the because of the size, the security, and the speed, they boot really quickly. It's just perfect for an IoT device. So it's kind of a bit of a trivial example. So I'm going to actually talk about some other things. Let's kind of talk about something that the MeRaOS end up doing. So they didn't want to reuse the existing TLS implementations. So they actually embarked on a new implementation of TLS from scratch. And they actually thought, oh, it's going to take a long time. But to their surprise, within a few months, they had a working, really working and very functional TLS module. And it was surprisingly tiny, only 10,000 lines of code. And compare it to OpenSSL, which had the Heartbleed. You can see it's like order of magnitude smaller. And this was written in OCaml. So how do they know that this is actually, how to check that this is actually works in the real world? So they came up with this really cool idea, which is a Bitcoin Pinata. I'll try to click on it in a second. And to basically lure in the attackers, they have put 10 Bitcoins, and I think each one of them is now over $400, into this unikernel, and they put it online. And they basically said, and I think they probably should Hacker News and other places, come attack the Pinata, and if you're successful, the Bitcoins are yours. So that's actually been up since 2015, and there have been hundreds of attacks on it. And the system is all basically the unikernel, the TLS protocol that they wrote, and so the Pinata, which is again written as a unikernel, the TLS protocol, and it's run on Zen. So the only external part that they used was Zen. So they basically, it's open source, so you can use the source to plan your attack. You can do anything you want. And they invited everybody to attack it. And after hundreds of thousands of attacks, nobody managed to get the Bitcoin. And so if I can maybe see if it works. It's not showing, right? Okay, how about we'll skip that, but we'll have the links. But actually, I want to show you both kind of the page that gives you the instruction to get to actually how to do, like how to get the attack, where are the ports, etc., as well as the bitcoins. The bitcoins have very interesting attribute that when you get it, there's a mark, like you will see when somebody got your bitcoin. So there's no way that somebody could have, they had to be signed. So there's no way that somebody could have gotten the bitcoin without them knowing. And nobody has got it, but they actually said that somebody donated. So if you look at the number of bitcoins right now, it's actually 10.06. So somebody actually decided to add a bitcoin. So we don't know, because if it's like they didn't tell the team, so we don't know. Maybe they just liked the project and thought it was really cool, so they wanted to donate, or maybe they actually use it as a way to try to understand how it works too, so they can attack it. But nonetheless, the Pinata is still up there, and it shows how this code that was written in several months has a very secure TLS. And again, together with the Pinata code as a Unikernel, actually survived all of these creative attacks. So another interesting thing to point here is, and this is kind of like, maybe an invitation, is just the way TLS has been rewritten in, Camel from MeRaOS. You could actually go protocol by protocol by protocol and rewrite them for this purpose using this technology. And it's kind of an invitation to continue to expand. And even though some of these protocols, they've been there for a while, and it seems, there has been so much art going into them, it's going to be so hard to rewrite. Here's an example how actually going in and rewriting is sometimes actually easy and good. So here's another interesting example. This one is actually not from MeRaOS, but I believe that actually there's this company is here in Oregon and a few other places. And apparently the term chaff is actually used in military, where you try to distract your attacker by placing other targets so they're not sure what to attack. And actually the company was commissioned by DARPA to create something new in this space for cybersecurity. And they came up with a very interesting concept, which is called CyberChef. And the idea is to introduce these lightweight nodes into your system that are kind of fake nodes, and they're trying to draw the attacker into them. So it's not kind of exactly a honeypot, but it's similar. Is that you have, if this is your if you have your network, then imagine many more nodes added to your network, and those nodes, they're actually this project is using a Unikernel called HalVM. And these nodes pretend to be other systems, unknown OSs, unknown services, to draw the attacker to them. Because normally when an attacker goes to attack a system, they'll try to find out what is a known VS and a known service that they have there, and from there they already know what the vulnerability of that OS and that VS and that service is, and they can continue attacking the network. So the concept here is that you spread all these fake services, and the attackers is now, one is the system from very known became unknown, because now it's big, has all the different services, and many of them are fake. Secondary, those nodes, they can pretend to be, like a known Windows OS or a known service, and by that draw the attacker to them. And again, now the system is being attacked and you can take action. So the use of Unikernel here is actually interesting, and in this case, the fact that you have this small kernels that you can, small apps and kernels that you can basically write anything in them is one use of the Unikernel attributes. The second one is the fact that they're so small. Now you can introduce them into your network without burdening it with like a much more significant scale. So, you don't have to add thousands of your regular nodes, but there's a really lightweight nodes that you're adding. This is pretty new, so we'll see where this is taking, this is going to be going. So another one is, this is actually our own Docker use. So we have introduced Docker for Mac and Windows, which is a very native way to work on your desktop to use Docker. And by the way, I know we have a beta waitlist, but if you need a priority access to it, I know the trick to get it. So you can let me know afterwards. And there, and I'm not sure how much it's known, but actually some Unikernel techniques have been used in the creation of this project. And and what happened there is like because they needed to work within like you need a virtual machine, right? You need a hypervisor. You want to run the Unikernel. You want to run your software inside, and you need to deal with like VPN and other attributes that the OS has. So they actually needed OS-like capabilities. And in order to do that, they actually went out and used all sorts of MeRaOS libraries and used them for the project. So this is actually an example where, if in the old OS world, you write this one big program and it's not very shareable, right? It's not kind of friendly. You can't like start tearing it apart and say, I'm just going to use this little module of it. By having OS libraries, what it actually enables is now you can use different parts of an OS for your own development. So you can become a very robust kernel developer by starting using different components that kind of at your disposal. So that's another cool attribute. And actually, this really helped this project because they had very significant issues there with networking, with VPN, and how to deal with that. And very quickly, they were able to, in fact, in a couple of days, were able to reuse something that they've had as part of MeRaOS. So where this is all kind of going and what are the steps remaining. So as you can see, Unikernel, hopefully you can see, has big potential, but there's actually lots of challenges that come with it. First of all, you still need to manage the life cycle of Unikernels. And you need to, if you have multiple of these, just the way we talked about it when we covered IoT, that you have multiple of these devices, might have multiple of these Unikernels, you need to be able to cluster and manage them. And you need to, again, manage the lifecycle for each one of them. And, like, how do you deploy them? So today, a lot of the deployment mechanisms are targeted towards bigger apps, but with small components like that, you actually get what is termed like dust clouds. There's like clouds with really tiny particles, really tiny apps running. And today the APIs are really not targeted to deal with a lot of small apps and many of them in smaller apps. And then you also need to be able to manage the images of Unikernels and being able to share them just the way you will want to manage, let's say, container content. There's also still work to do to make them easy to build. There's no IDE. First of all, there's cross-compilation that you need to do. And there is no IDE. You need to integrate with existing IDE systems to make it very easy to start from your code and build a Unikernel. And then while these libraries we talked about, there's many libraries. A lot of the functionality is exposed, but certainly not all of them, not all of it. So there is still a lot that needs to be written for it to be really fully functioning for every single app. However, when you think about it, these were all like classic problems that are solved by Docker. And, just the way that containers have been there for a long time. Actually, unikernels have been there for a long time, at least the concept. When you think about it, I mean, how many of you knows what a NetApp filer is or a Cisco router? Many of them have a very specialized OS written for them. So this concept of specialized OS is not necessarily new, but the concept of taking a library and being able to create a kernel very easily and make each one of the developers a kernel developer, that is kind of really the new concept. So that is new. And just the way Docker have worked to bring containers as something that access, again, containers also has not been a new technology, but just the way they help to bring containers, a technology that is popular and used by everybody. What we want to do is do the same for this technology and actually tie them together. And there are some benefits in how you can tie them together. So you can think about unikernel as what you want to use in the extreme and in the endpoints. I guess kind of where this is going, you're going to see more and more of these technologies being combined. So if you're using, the good news is if you're using containers, you're on the right path to get more and more access to this technology. So I guess continue doing what you're doing. So that's really kind of what I want to end the talk with is, not necessarily new technology, but super useful. How do we make it accessible and usable to all of us and all of the developers and have it accessible in a normal, non-kernel developer hands is what we're going to be embarking on. And, before we go to Q&A, I do want to thank a bunch of people. The Bitcoin Pinata, the developers that created Bitcoin Pinata, the Unikernel Docker team, the names are here. Actually, a couple of them helped me with the presentation, and Neil and Morty and Richard, whose nickname is Mort. They're actually located in Cambridge and been working in a lot of collaboration with the university there. And the wider unikernel community, there's actually multiple unikernel efforts, and there's a big kind of movement around that. That's it.